All right. All right, so I don't think we need to review what we just talked about because I kind of did that in the homework there. So we can instead just kind of jump right in here to our next section. All right, the next section we're going to be looking at here is section 9.7, error approximation. Okay, and this is our last section. We're going to stay at 9.7 for 2 days. All right. Error approximation, section 9.7. Spent 2 days in this, right? And basically, we're doing 2 days because there's kind of like two different ways that we can approximate error. Okay. So anyway, let's kind of jump in here, like I said. So one of the bigger uses of Taylor polynomials, right? The way we've been using it is to approximate values of a transcendental or a trigonometric function, right? This is, in some senses, depending on the model of your calculator. This is exactly how your calculator actually calculates sine and cosine, tangent, ease. Okay, it actually does it this way, not using, some actual sine function. It just uses the Taylor polynomial to match it, kind of thing. So, the problem, of course, okay, is that we have these are approximations, right? They're not exact, but the idea is, of course, in your calculator, it just does so many, a Taylor polynomial that's so long that the decimal point that we see on the screen when we type in the answer, right, that is accurate. It just, the error, beyond it goes, or where it starts to go off is like way beyond what we actually see on the screen, kind of thing. So we can, use that information and stuff like that. All right. Let's see here. Where did I have this? Oh, right, I'm in the wrong section, that's why. I'm looking at this thing right there. Here we go. So what we've got right here then is what you could maybe call the actual function, right? So f of c, that's like the actual value. And that's equal to then our approximation. Okay. But of course, our approximation is not quite right, and so then we'll take the approximation, and then there's some other like remainder, you could call it, or slash, error here. Okay. So the actual function value at c is equal to our approximation using that Taylor polynomial of, however many degrees you want, kind of thing, and then plus then a remainder or error. Okay. So the remainder then, if we kind of manipulate this equation around, right, the remainder or error, right, r sub n of c is equal to the difference of the actual value minus the approximation. Okay? So, in other words, this can be expressed as error is equal to the absolute value of f of c minus p sub n of c. Okay? Or in other words, the actual minus the approximate. Okay, and you see this idea show up in other disciplines, right? In high school, I would say even, right? So like in the science and stuff, you probably should see, some sort of error calculation. I feel like I remember doing that in other classes and things. So there's that. Now, with the idea of putting the absolute value in there, right? Then we could just as easily say p sub n of c minus f of c, right? That's going to be the exact same value. If you switch the subtraction around, because you're in absolute values, it's still going to keep it, the same. It's still going to keep it the same, number, same value, right? Since we're taking the absolute value, the subtraction you can switch, positions or whatever there, and you still have the same value. Okay. So, but that's our error. How much we are off by. Okay. So we're going to find this error, like I said, using one of two methods. Okay, and it depends on whether or not the polynomial alternates. Today, we'll be focusing on the one where the polynomial alternates, and then tomorrow we'll look at the one where the polynomial does not alternate. Okay, so alternates today. The one key thing I want to kind of keep in mind here, right, is that we will never know, or we're going to kind of pretend here that we don't know the actual value in some of these situations. Okay, so it's kind of like I mean, in some of these cases, right, you can just type into our calculator and get the actual value here. So in a certain sense, we have to kind of understand we're not going to know the actual value, right? And also, the best we're going to be able to do here, right, for these things is to not get the actual exact error, but to get an approximation of the error, right? Because if you take a guess at something, right, so a polynomial, a Taylor polynomial, for example, is like a guess at something, all right? If you take a guess at something and then someone tells you, your guess is off by 5, well, then you know, so that's your error would be like 5, right? Then you know exactly what the actual value is going to be, right? So it's kind of like, well, then we just, add 5 or subtract 5, depending on whether, we're off by more than 5 or less than 5 kind of thing, and we get our actual answer. But for our estimation, or today, our estimation, error is going to be an estimation, okay? It's like, you can't ever really say exactly how far off you are, because then you know the exact value. And the whole idea here is that we're estimating in the first place, and so we'll just get we'll kind of like limit the amount of error that we have. We'll be able to say our error is less than this certain amount kind of thing. So that's the best we're going to be able to do. Okay? But of course, we'll also do some problems where we know the actual value, so then we can actually see that it does in fact work too. So anyway, all right. If a series, the sum from 1 to infinity of a sub n, is alternating and decreasing in absolute value, and the limit as n approaches infinity of a sub n is 0, then the series converges. Okay, so we need to have, and these are bolded for a particular reason here. We're going to be using these words in a little bit, okay, and part of our kind of justification about why we can use this idea here. If you look at the partial sums of the series, it will bounce back and forth around the actual sum. Okay, so to kind of show this, we're going to start with kind of a basic example here. Okay, so here's a geometric series, right? -1/2, and it alternates too, right? We can see because the negative there, so it's going to be +1, -1/2, +1/4, -1/8, +1/16, -1/32, so on and so forth, right? So we know this is a geometric series. And further, we know that this geometric series will converge or diverge. Converge. Because why? So yeah, the common ratio here, which is what? What is the common ratio? -1/2, right? But we can use the 1/2 there because it's going to go in the absolute value. So yeah, because the absolute value of -1/2 is less than 1, so that's, we know that. And then because this is geometric series, we further know what the sum is going to be, right? The geometric series, we can find that sum. It's, our first term, so 1 over, and then 1 minus our common ratio of -1/2. And so that's really, plus a +1/2 there instead, right? Multiply everything through by 2, you get 2 over 2 plus 1, so you get 2/3, okay? So, knowing that the series is geometric, we already know that the series adds up to 2/3, or if you like, 0.6 repeating there. So again, the importance of the error approximation here is not that great. I mean, like the use of it's not that great because we already know what the exact value is. But again, we're going to kind of get you the idea. We're going to take something that we know the actual value of, and then kind of build this idea of error, how we can kind of understand the error and stuff like that. Okay. So again, let's imagine that we didn't know what this series equals, right? And we're going to approximate using the first few kind of partial sums. Okay. So in other words, if we use the first partial sum, just the first term, that's equal to 1, right? And that is one approximation, of our actual, -1/2 to the n, right? This is kind of like what we do with Taylor polynomial, right? We start with, okay, there's like a degree 1 kind of thing you can imagine. First term. Well, let's try now. Do the second partial sum here, which would then be 1 minus 1/2. Okay? 1 minus 1/2, that's equal to 0.5, okay, which again is an approximation of the sum of that -1/2 to the n. Now our first partial sum, how far off from the actual value was it? A third, right? 1/3, right? We've had 2/3 was the actual sum. 1 is off by 1/3, okay? But then we do the next partial sum, so 2 terms, right? The partial sum of 2 terms there, and now we're at 0.5, okay? Now how far is 0.5 off from 2/3? So yeah, a sixth, right? Because one half is 3/6, 2/3 is 4/6. So it's only off by a sixth. So we went off from 1/3 now to off by 1/6. So we're closer, right? We're better. So if we go again here, S sub 3, which is then 1 minus 1/2 plus 1/4. Well, it's what we had before, the 1 minus 1/2, which is 0.5. We're going to add a fourth to it, so it's 0.75. Okay. And so now we're off by what? A 12th? That's 3/4, 2/3, so 8/12, and 9/12. So yeah, we're off by a 12th now, okay? Even closer. And again, this is an approximation of that negative 1/2 to the n. And we'll do one more here. 1 minus 1/2 plus 1/4 minus 1/8, which is exactly 0.625. Again, approximating that sum from negative 1/2 to the n there. And we get 0.625, which is yet again even closer, right? Even closer. All right, even closer still. Okay. And we started here, right? Because of this alternating idea here, we started 1, was that over or underestimating the actual value? Over, right? So we are over a third. We are over by a third. But then the next term, because that minus 1/2 came in, right? We alternated the sign. We went from overestimate to now, what was this one? Under by a sixth. And then the third term here was over or under. Over by a 12th, right? And then the next one was under by, and then however much that would be, but it's going to be under, but less than earlier, right? And so what we kind of see happening here, if you like imagine kind of graphing this thing, let's say that 2/3, okay, let's say this is 2/3 right here. Okay, and so we'll graph like the nth partial sums here, and then like these will be their values here. And again, I'm just going to kind of like approximate these here. So let's say, for example, our first partial sum there, S sub 1, okay, well, its sum was 1. So we kind of went like something, I don't know, if that's 2/3 and like 1/3 more, maybe it would be up like here. Something like that. Okay. And then we'll try graphing S sub 2. What does S sub 2 introduce? Well, it still has the 1 from S sub 1, but then it introduces a minus 1/2. So from this 1, we're going to go down 1/2. And so about halfways would be, I don't know, something like right there maybe. Okay. And so you can see, right, we're now closer, right? Because we're shooting to get closer to this actual value. And sure enough, we are in fact closer. You can kind of see it visually there, right? And then we'll do the same thing for S sub 3 here. So S sub 3 is 0.75. So that's like 3/4. So if that's 1/2, then half of the half would be like right there, maybe. Yeah, something like that. Okay. That's not quite so obvious, but it is, a little bit closer still. And then 0.625 for S sub 4, which, I'm just going to put it here somewhere. I don't know. Okay. And so the idea is, as we proceed, we get closer and closer, okay? And in fact, we are, but we're also alternating above and below the actual value there, okay? So how are we going to use this then to estimate the error, right? It's kind of like tricky because we already know the actual value here. We were able to come up with the actual error, okay? And if you know the actual error, then you can find the actual value, right? I mean, that's just a case of that. You need to know the actual value in order to find the actual error. So the estimated error comes in. Well, here's the idea what we're going to be doing here. So that first partial sum, right, it was 1. And then what did we do? We took that 1, we subtracted 1/2. So that means and we knew we crossed through the value 2/3 there, right? So in other words, the error was going to be at most 1/2, right? The 1 here, if we subtract 1/2, we go through the actual value. So we know the error will be at most 1/2, but probably less than that, right? Because we actually crossed through it before that. Then for the next term, S sub 2, right, to cross through that actual value again, we added the 1/4 there. So at most, the error from the second partial sum will be at most 1/4, right? But actually it's less than 1/4. Okay, but of course we don't know the actual, we're just estimating here. And then for the third term, okay, the value here was exactly 0.75, okay, but then the next term we got was minus 1/8, and that would again take us to, that's like our error there. So our error is diminishing here, or the approximate error, okay, with each next step. It brings us past, and they're getting smaller and smaller, okay? And so these are where we're going to get this idea of the approximating the error, okay? So we'll go to this next thing here. So if one partial sum is larger than the true value, subtracting the next term will cause the partial sum to be smaller, and adding the next term will cause the partial sum to be larger, and so on and so forth, right? So again, we started with a positive term, subtracted a certain quantity, then added a certain quantity, then subtracted a certain quantity, like that. Okay. The error is the difference between any of the partial sums and the actual value, but by adding the next term, the partial sum will go past the actual value. So therefore, the maximum error will always be less than or equal to the first or next neglected term in the series. I feel like it should be non-neglected term in the series, but anyway. Okay. So again, this only applies though to convergent alternating series that decrease in absolute value to 0, right? Because if this wasn't alternating, right, we would, instead of going like up, down, because we're adding and then subtracting and then adding and then subtracting, right, it would continue to add. So we wouldn't be able to use this kind of idea here. Okay. But the key idea here is that the maximum error, the most we're going to be off by, is less than or equal to the next term. Okay? The most we're going to be off by is less than or equal to the next term. And that's what I was trying to show here, right? 1 was the first partial sum. The next term in that was -1/2, and we are off by less than -1/2, right? Because there's -1/2, it takes us below the actual value there. Likewise here, from S2 to S3, right, we are off by less than 1/4 because 1/4 takes us through the actual value. And same thing here, from S3 to S4, we're off by less than 1/8 because, again, 1/8 takes us through the actual value there. Okay, so questions on any of that? All right, so that's the concept, okay, and maybe I've just beat a dead horse here. So our formula we're going to use here is max error for these alternating series, maximum error, which is equal to f of c minus p sub n of c, okay, will always be less than or equal to the absolute value of the next term. Okay. So the difference between the actual value of the function at c and the estimated value using our Taylor polynomial will always be less than or equal to the value of the next term. So in this case, it would be n plus 1, right? Our nth term polynomial there would be, n plus 1 term. Okay? So let's see this actual practice, okay, now that I've bored you all to death with the concept here. Let's see an actual problem, all right, and see like what it actually looks like in practice. So given g of x equals 6 over 2 plus x, write the first 4 non-zero terms for the Maclaurin polynomial and the general term for g of x, okay? And then using this polynomial, approximate g of 1 and determine the maximum error. So there's kind of, like what we're going to be, shooting for right there, stuff that we just talked about. Everything else, we can do that no problem, right? So when we look at g of x here, okay, g of x is equal to 6 over 2 plus x. What does that look like? It looks like what? It is geometric. Yes, it looks like it is geometric, and in fact, it is geometric. Okay. What kind of clued you in there, Lander, that you thought it was geometric?
2 plus x.
Yeah, okay, so you have a number over something plus x, but of course it's not quite in the right format, right? We have a little bit of manipulation to do. Okay, so for example, we don't want 2 plus x, we want 2 minus x, sorry, 2 minus something, so we're going to do minus then a negative x like that. Okay. And then what else is still off about this being an appropriate geometric format? It has to be a 1, not a 2. Exactly right. So we'll divide, multiply the top and bottom by 1/2, divide the top and bottom by 2, however you want to think about it. 3 over, 1 minus negative x over 2. Like that. All right? So then our geometric series here, the sum from n equals 0 to infinity, And so our first term is going to be 3, so 3 is going to go out front. And then this is the negative x over 2 to the n. Right. But I'm going to pull out the alternating piece here. Again, I like to pull out that alternating piece. So we'll make it 3, negative 1 to the n, positive x over 2 to the n, like that. Okay? So I'm going to let you guys then go ahead and write the first 4 non-zero terms. So you guys take care of this piece. Write the first 4 non-zero terms of this Maclaurin polynomial and the general term. Okay? Well, I guess we technically already have the general term because I gave it to you right there. All right? So there's that. But you can then approximate g of 1. So I want you guys to go ahead, write the first 4 non-zero terms for this. Okay, and then use that to approximate g of 1. And you can use your calculators if you really want to figure out that estimate for g of 1. Okay, so go ahead, write out the first 4 terms of that series. So I will do that here because I'm going to run out of space. Again, once you've got your first 4 terms, then use those 4 terms to estimate g of 1. Okay? Use those first 4 terms to then estimate the value at 1. And then use that to estimate at 1. Let's estimate when x is 1. If you want to use a calculator, use small. 1, exactly right. So we minus then 3x.
Yeah, we have to watch it.
Wait, there's a book? I've watched the movie multiple times. Yeah, it's
So funny.
I was listening to college, and they're very good at this college, but they're just like smart.
She looks like Dodge.
But there's an obvious benefit to it over not having a
No, we watched.
Well, and again, there's always exceptions. It's definitely possible, but when we look at like an aggregate kind of population,
That was the time.
definitely benefits to getting a degree.
I have a question.
Yep.
How long am I?
When aren't you?
1.875. It should have been.
Oh, I didn't.
So that's right. Yes. Now plug in 1 for x's and
Wait, how do you know? Oh,
Well, I don't wanna.
that's right.
I, right?
Sorry. Oh, yeah, calculator time. Experimental math.
Through mental math. There you go. That's the spirit.
We're not calculators. We shouldn't even have to do this. Mr. Weird.
What's the trouble? This whole thing we'll say is calculator active today, okay? So
What about on test?
I think so. Yes, I think so. Yes, these do tend to be when you actually when we do the practice for responses on Friday, you'll notice these problems tend to show up as like the very last pre-response question, which is good news for us because that means everyone else will be mentally exhausted, but you guys won't be. You'll be ready to go for that last one.
Oh yeah, ready to go.
Hello? Hey, I'm well. How are you doing? I do. I can do. Mm-hmm. Bye. Julia, Miss Southern wants to see you. If you're not busy right now. All right. So here's our sum. Here's our sum, right? Again, we're using that. There's the first four terms of it. Okay, first four terms, which is again approximation of g, right? Those first four terms. And then using that then to approximate g of 1, we just plug 1 in for the x's, right? This polynomial is approximating the actual function g, so we plug in 1 to then get the approximate value of g at 1. 1.875 is what we get. Okay. But we're going to then, okay, sorry, so we got our estimation. So now what we're going to do then is determine the maximum error. So here's the new stuff, right? So this is all old stuff right here. It's nothing, nothing crazy. But now we're going to determine the error because we know that this is going to be off by a certain amount. Okay, it's not exactly right. We estimated this, right? It's an estimation. So the max error, okay. And before we can go and apply this idea of max error, we need to state here, this is like your justification, kind of like, when you go to, determine a relative maximum, you state that, okay, well, since f prime is, positive, and then it changes to negative at this point kind of thing, therefore we know that there is a, relative maximum. For this case, right, we need to identify, well, this is a alternating and decreasing an absolute value function. And so we're just going to state that, okay? I mean, is this function alternating? I mean, yeah, clearly it's going to be, this power series here is alternating. Also, is it decreasing in value as you go? Yeah, right? I mean, we're taking, yes, we're going to be squaring x, we're going to be dividing by 4, 8, and so on and so forth, okay? So it's going to continue to decrease in value there as long as, well, that's a good question, though, because the actual term, x there, but, decreasing in absolute value to 0. Okay, so yeah, the terms are getting smaller and smaller as we go. So anywho, so let's take a look here. So since g, I'm going to put that in here first, actually, before I put max error. So since g is alternating and decreasing in absolute value to 0. Okay, since g, or our power series there, is alternating and decreasing absolute value to 0. Okay, the terms are getting smaller and smaller. Then we can identify this max error. Okay, so now I'll write max error there. Okay, so the max error, remember, it's that idea of g of 1, the actual value, take away then, in this case, it's a third degree Taylor polynomial, right? Or a third degree Maclaurin polynomial. Okay, so we'll do p sub 3 of 1. Okay, so again, it's actual minus the approximation there. That's the difference. Okay, but that, of course, is the formula for the actual error. We don't know what the actual error is, so we're going to use this though to determine, our quantity that we're off by. And that's going to be less than whatever that next term is going to be, absolute value of the next term. Okay? So how much we are actually off by must be less than or equal to that next term. Because remember, every time we add that additional term, we go through the actual value. Okay? If we add the additional term, we're going up through the actual value. If we're subtracting that next term, we're going down through that actual value. Okay, so and that's why we just put the absolute values in to kind of eliminate the sign idea. Okay, so we went up to the third term here. What would the fourth term, what is the fourth term in this case? Right, if we had the third term, the next term would be the fourth term. What would the fourth term be? What would the format of that be? Yeah, it would be 3x to the fourth over 16. Yeah, so the next term here is 3x to the fourth over 16. And we're going to evaluate that at that same x value, x equals 1. Okay. So, again, just kind of moving things over here. So in other words, the actual value of g at 1 minus our polynomial approximation, the third degree polynomial approximation, which as we said was 1.875, if you remember, right? That actual difference is going to be less or equal to the value at that next term there, which is just going to be 3/16. Okay, which coincidentally happens to be, and this isn't going to always be the case, but happens to be 0.1875. Okay. And so that's it. The maximum error then, the most we're going to be off by in this third degree polynomial approximation, the most we're going to be off by is 3/16, but probably less than that. So that's our maximum error there, is 3/16 or 0.1875. All right. Questions on any of that? Okay. So, of course here, this was all kind of just an exercise, not in futility here, but just an exercise in, kind of like basic understanding because, well, what is the value of g at 1? Yeah, so it's going to be 2, okay, because we know the function g here, right? So we could just find g of 1, and it's going to be 2, okay? But you can see here what the idea is. So 1.875, okay, we know g of 1 is actually 2, okay? So what's the error then? What's the actual error? Well, you do 2 minus 1.875, and we get 0.125. Is 0.125, is that less than our maximum error here of 0.1875?
Yeah.
It is, right? Okay, and so you can see the process works, all right? In other words, we, in this case, we know the actual value, so we can find the actual error, and then that is certainly less than our estimated, maximum error there. So we can see that it does in fact work there. Okay? And again, and assuming we don't know g then, so because of this, right, we can say, all right, well then, g of 1, I'm going to kind of move it up here because I'm running out of space. G of 1, the actual value, okay, again, since our maximum error is 3/16, we can go 3/16 above that estimate of 1.875. We can go 3/16 below that estimate of 1.875. So it's less than or equal to, 1.875 plus 3/16, or it's going to be greater than or equal to 1.875 minus 3/16, right? That gives us kind of the range there, okay? The difference between the actual value and our estimate of 1.875, it's going to be off by 3/16. So then that means g of 1 is going to be between 1.875 minus 3/16 and 1.875 plus 3/16. Okay, the actual value g of 1 gives that range. Okay. So there's that. Questions on anything there? Maybe I'm just over-explaining it. I don't know. So we'll keep moving then here. Let's try example 2. All right, so for example 2 here, given f of x equals sine of x, so a new function, we got sine of x, write the 5th degree Maclaurin polynomial and the general term for f of x. Using this polynomial, approximate sine of 0.1 and determine the maximum error. Okay, so why don't you guys go ahead, write that 5th degree Maclaurin polynomial for sine of x, right? That's one of those functions we should be, familiar with. We should also be familiar with this, general term here, hopefully, right? So go ahead, take like a minute, and just write that 5th degree polynomial there. Okay, and then if you want, go ahead and approximate for a sine of 0.1. Okay, so all this should be familiar. Okay, up to the determining the maximum error part. fifth degree term, not 5 terms. Fifth degree term. Yeah, fifth degree, not 5 non-zero terms. Fifth degree. So, hint, there should be only 3 terms in your polynomial to get up to the fifth degree. Yes. Not 5 terms. Fifth degree. So you should only have 3 terms in your polynomial. And then, of course, use that to approximate sine of 0.1. Use that fifth degree polynomial to approximate sine of 0.1. And again, calculator active. Feel free to use your calculators.
Hold on.
Okay, so hopefully you got something like this, right? General term, right? We know sine is going to be that, the odd degrees there. Okay, so for the fifth degree, we're going to have x, 1 x to the 1 over 1 factorial minus an x to the 3 over 3 factorial plus x to the 5 over 5 factorial, so on and so forth, right? If we wanted to keep going, but we only need 5 degrees, or fifth degree terms, so we're there. Okay, and then there's the general term, right? Again, that's that, we hopefully have that still down, right, in our head somewhere, okay, to use. I did identify the general term here. And then sine of 0.1 is going to be approximately, right, that fifth degree Maclaurin polynomial at 0.1. And so we just plug 0.1 in for those x's to then get that estimated value of that. Okay, since f of x,
Do I have to write that every single time?
if you're going to be doing error, yes. If it's for a justification, if it's for a free response question, yes, you need to show that you considered this. Absolutely. So since that's going to be alternating and decreasing in absolute value to 0, so since f of x equals sine of x is alternating and decreasing in absolute value to 0, the max error, which again is the estimation of the actual error here that we're going to write out. Again, actual minus approximate. But again, remember, these could just be flipped, right? We can flip those around because it's in the absolute value, so you could also say approximate minus actual there. In the absolute values, it'd be the same thing because it's in absolute values there. It's going to be less than or equal to our next term. Okay? What is our next term in this situation? So exactly, it's going to be, I'm going to do the general idea first here. So yeah, and so technically negative x to the 7 over 7 factorial, but because we're in the absolute values, you can kind of drop that idea. Okay, and again, evaluated at x equals 1 then, It's going to be, yes, negative 1 to the 7th over 7 factorial. Sorry, 0.1. Thank you. 0.1. Yes, negative 0.1 to the 7th over 7 factorial. Okay, which we do that in our calculators here. So, math, you can do the absolute values in there if you want. Negative, no, negative 0.1 to the 7th over, goodness, 7 math factorial. There you go. Okay, and yes, that is correct. 1.984. What does that e negative 11 mean?
It goes 11 levels out.
So times 10 to the negative 11. This is like scientific notation you can think of it as, okay? So yeah, that's equal to then 1.984, you know, 1, 2, 6, 9, 8 times 10 to the negative 11th there, okay? So that is the maximum amount of error that we have. Maximum error is that tiny number, okay? Teeny tiny value there. That's our maximum error. That's the furthest we're going to be off by with this 5th degree evaluation, this 5th degree Taylor polynomial that we used. Okay, that's pretty crazy, right? That this at 0.1, you know, is going to be that close. Okay. So, by the way, what is sine of 0.1? Okay, so if you actually go on your calculator and type in the actual value, sine of 0.1, okay, you get this, 0.0998. So this is equal to, I'm going to put big old equal signs there because that's exactly equal to, well, I guess I shouldn't say exactly because the decimal keeps going, but. Okay, there's what our calculator says is sine of 0.1. Remember p sub 5, right, our Taylor polynomial, Maclaurin polynomial, at 0.1. Okay, we got for that to be 0.0998334167. Right? At what decimal place does that occur? Well, if you look here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and 1.9841. So that is, if you so if we subtract here, let me just do the subtraction. All right. So 0.09. I'll do the real minus the approximate there. 0.9. I guess I can just do it this way. 4, 3, 3, 4, 1, 6, 7. So you get that, you see you're off by about 5.3, okay, or negative 5.3, e to the negative 11, okay, which is between, well, this is less than that value right there. So, okay, or it should, I must have missed it. I missed something here. Let me try that again. 0.099833416 minus 0.09983344167. Okay, so negative 1 e to the negative 10th. Yeah, so it's off by 1 times 10 to the 10th. Okay, so that's the actual error there. But there is the approximated error. Okay. Questions on any of that? So there's the actual, the estimate that we're off by. All good? All right, let's keep going here then. Number 3. All right, so go ahead, letter A. All right, if f of x is equal to e to the negative 2x, well, maybe I'll help you guys with this one here. So e to the x, right, we know what that is. That's approximately, 1 plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial, And that's, of course, the third degree for e to the x, okay, which we know is, this, but we want e to the negative 2x, okay, which means what do we do with all of our x's? Oops, Mom. what do we do with all of our x's then? Replace them with just with a negative 2x. So it's going to be then 1 minus 2x over 1 plus 4x squared over 2 factorial minus 8x cubed over 3 factorial. And then that's our p sub 3 of x there in this case. Okay. So just building that e to the negative 2x using our power series e to the x there. Okay. Using p sub 3 of x, approximate f of 0.5. So again, f of 0.5 will be approximately p sub 3 of 0.5. I'm going to plug that 0.5 in, okay, which is equal to, well, and then we'll just type this into our calculators here. So 1 minus 2x plus 4x squared over 2 factorial minus 8x to the third over 6. I'm not going to do the 3 factorial. So 0.333, it's 1/3. Okay, or 0.3 repeating. That. Okay. So then show that f of 0.5 differs from p sub 3 of 0.5 by less than 1/20th. All right. So that means we're going to, again, need to look at, well, what do we need to look at here? This maximum error, right? We want to show that they are different. We want to show the actual differs from the estimate by less than 1/20th. So we want to, again, get that maximum error and show that it's, less than that. So, right, we got to write our sentence first. Don't forget that. Since f is alternating and decreasing in absolute value to 0, okay, then the max error here which again is the actual value of f at 0.5 minus the Taylor approximation at 0.5. Will be less than or equal to, and again, the absolute value of this next term. Well, what would the next term in this particular Taylor polynomial be?
120. 240.
So, right, it's going to be 1/20th the final answer. Well, so we want not on 1/20th, not 1/20th, sorry, no, not yet, not quite. So, yeah, what's our next term going to be? So it went from 1 to minus 2x over 1 plus 4x squared over 2 factorial minus x to the third over 3 factorial. So the next one's going to be what? 16x to the 4 over 4 factorial. But instead of x, I'm going to put in 0.5. Okay? 16, I'll just put the 0.5 in for x there. Okay, so again, using our calculators, we'll just type this in. 16 times 0.5 to the 4 over 4 factorial. So that's what? It's 24. Okay, math, enter, enter. 1/24th is what we get. And I wrote 1/64th. There we go. Okay. So according to our calculations here, the maximum error is 1/24th. We're trying to show that these two differ by less than 1/20th. Is 1/24th, is that less than 1/20?
Yes.
Well, yeah, of course the answer is yes, right? And if you don't believe me, right, we can cross multiply here and say, is 20 less than 24? And so yes, that's true. So yes, that's true. Okay. 1/24th is less than 1/20th. So they do differ by less than that. Okay. What's the actual difference? Well, again, if we wanted to, we can actually just check and see here. So again, I can do e to the negative 2 times 0.5. Okay. And we end up with this, and I'll subtract 1/24th from that. Okay, and I think I messed something up here. Let's see here. E to the negative 2 times 0.5, or not minus 1/24th. Sorry, I want to use the estimate there of 1/3. I'm sorry, I did the wrong thing. So e to the negative 2 times 0.5. Okay, so there's the actual value of e to the negative 2 times 0.5, and we'll subtract our estimate value of, what we say, where was it? Oh, 1/3 there, so minus 1/3. Okay, so there's the actual error from the actual value subtracting away our estimate there, and what we said would be the maximum error was 1/24. Okay, you can see that the actual error is going to be less than our maximum error there. Okay, just by that. Okay. All right. Questions on anything so far? All right. Number 4 then. The Taylor series for function f about x equals 2 converges. Or to f for -1 less than or equal to x less than or equal to 5. This is like that interval of convergence there. Interval of convergence there, if you like. Okay. The nth degree Taylor polynomial for f about x equals 2 is given by this. Okay. So the good news is here, right, they're giving us the Taylor polynomial. We don't have to come up with it on our own using, power series or geometric series, stuff like that. Okay, they're giving us the actual Taylor polynomial format right there. Okay. And again, it's about x equals 2, and you can see there's your, the x minus 2 there for that centering idea too and stuff like that. What is the smallest degree n of the Taylor polynomial that guarantees that f of 3 minus p sub n of 3 is less than or equal to 1/100? Okay, so in other words here, we're trying to show that so what is this talking about here when it's asking us this question? We're trying to guarantee something about, well, what is this format? It's maximum error, right? It's maximum error, yeah. So we're trying to show here that the maximum error, we want to kind of come up with a Taylor polynomial, okay, of degree n that has, it's the smallest degree n, so like the first kind of, the earliest Taylor polynomial that gives us this guarantee that our error will be off by less than, at most, less than 1/100,000. Okay, but of course the format for maximum error here is going to be f of 3 minus p sub n of 3 less than or equal to, again, that next term. Okay, and the way we're going to kind of do this here is guessing and checking. Okay, we're going to guess and check. Okay, so you want to guess 4? Is that what you said? All right, let's guess 4.
No.
Guess. What do you want to guess, Mike? 3? All right, 3. Well, let's try 4 here and see if it works first, and then maybe we'll see if we want to go to 3 or not. Okay. So it'll be f of 3 minus p sub 4 of 3. Okay, and again, that's the actual error. We know that actual error is going to be less than or equal to. And again, so over here, again, is our maximum error. And again, that comes from the next term. So if Mario chose n equals 4, then our next term would be when n is equal to 5. 5, right? Just the next term. So what comes after 4? 5. So we're just going to then evaluate the fifth term here, right, and see what we get. So it'll be -1 to the 5th. Okay. It's not really necessary here for me to put that -1 to the 5th in there because it is in the absolute values, but I'm just going to put it in just for completion's sake here. In for the x, what should we put in for x? 3, right? Because we're evaluating this at 3. And then the k value, again, is going to be to the 5th here. Over, I could, okay. 3 to the 5 times 5 squared plus 1. All right. And we're going to type this mess in our calculators. So it's going to be very clear that we get 1 in the numerator there. But then whatever that 3 to the 5th is. Okay, so we get 1 over 6,318.
No.
Did I mess that up?
That's what I got. That's what I got.
3 to the 5th?
I got it.
Oh, you did get it, okay.
No, you did.
Yep, 6,318. Okay. So, did Mario choose correctly?
No.
And again, he just guessed. Why didn't he choose correctly? What indicates that we didn't choose correctly here? Right, this error, right, this maximum error, 1 over 6,318, is greater than is more error than 1 over 100, 1/100,000, right? This fraction is greater than this fraction, and so we're kind of we're allowing for more error than we want to. So this is a bad guess.
Let's do 7.
Okay, so let's not do 7. Let's do.
Yeah, let's do the correct answer. But
16.
Well, I'm going to jump to 5, and then I'll show you 6 here. 6 is the correct answer here, but I just want to kind of show you the process here. Okay? Because here's the problem. If I jump straight to the 6th, if I just jump straight to the 6th and it said, oh, it works, well, we still have to check to see if 5 works too, because we don't want just anything that works. We want the smallest degree n of the Taylor polynomial that guarantees such is true. So if 6 worked, we would have to still check to see if 5 worked. So I'm just going to quickly, write up the 5 here. A p sub 5 of 3. And again, for the next term, then if we're checking to see if the 5th degree Taylor polynomial works for us, we are actually going to check the 6th term to see if it's less than, or if it's less than 100,000 there. So again, -1 to the 6th, 3 minus 2 to the 6th, 3 to the 6th, 6 squared plus 1.
Wait, isn't it? Oh, wait, never mind.
Okay.
Equals.
And so that should equal, and just I'll give you this one here. It's 1 over 26,973. Okay, which again, is that less than or equal to 1/100,000?
Nope.
No, right? That denominator is not quite there, right? That fraction's going to be too big. The fraction's going to be too big, too much error. So no. So let's try the 6th degree Taylor polynomial here. See if that gives us a smaller error, or the right amount of error there. So -1. Again, the next term then, if we're checking the 6th term, we have to check the next term, which is the 7th term. Okay. If you type that mess in your calculator, you get 1 over 109,350. Is that less than or equal to 1/100,000? Yes. Okay, so n equals 6. Okay, so would 7 work? Yes, 7 would give you less error than that. 8 would give you even less error. 9 would give you even less maximum error. But the problem is we wanted the first degree, the lowest degree. So degree 6 there. That gives you, an error less than 1/100,000. Okay. So n equals 6. Questions on any of that? Can we stop? Soon. We can stop soon here. After this one right here. All right, number 5. Okay. So, the Taylor series about x equals 4. So now we're centered at x equals 4. For a certain function f converges to f of x for all x interval of convergence. The nth derivative of f at x equals 4 is given by this. Okay, so is this our Taylor series? No, this is just the nth derivative of the function that we're approximating. So in other words, we kind of have to build this Taylor polynomial here, okay, 3rd degree Taylor polynomial. So if you remember, right, way back when we were doing this, right, we were trying to find, it would be f of 4 plus f prime of 4 over 1 factorial times x minus 4. And we want 3rd degree, so plus f prime of 4 over 3 factorial times x minus 4 to the 3rd, right? Remember we did that? So we have to do that here because we're not given the actual series, we're just given the nth derivatives and stuff like that. And again, it's centered at x equals 4 there, so that's why we have to do the Taylor polynomial, right? Okay. So I'm even going to do, excuse me, I'm even going to do that side calculation over here that we used to do too, just because I think it's going to be easier to write it out here some, spread things out a little bit. Okay. What is f of 4 going to be? 1, right? They're giving us that piece of information right there. F of 4 is 1. So it's just 1. F prime of 4 Well, now where do we go to find f prime of 4? We're going to go to this thing right here. Okay? So if we're trying to find f prime of 4, what is our n? 1, right? F in the parentheses, right? That means the number of the derivative. F prime is the first derivative, so 1 goes in for n. So we're just going to plug in 1 for n here. So we're going to have a negative. 1 plus 1 is 2. Factorial will still be 2, so negative 2 over 2 to the 1, which is just 2. Okay, in fact, I'm going to leave things unsimplified here, and you'll see it'll be helpful for writing that general term. Okay. So then what will the next term be? Well, f prime prime, which is second degree, so n is now 2. So we're going to have a positive 3 factorial over, and then 2 to the 2, which is 2 squared there. I'm just going to, again, I'm not going to simplify out the powers. I'm just going to make it 2 squared. And then third derivative of f at 4, now n is 3, and so it'll be a negative again. 3 plus 1, so 4 factorial over 2 to the third, like that. Okay. So our polynomial is 1 minus 2 factorial over 2 over 1 factorial, x minus 4. F prime prime of 4, which we got right there. So it's going to be 3 factorial over 2 squared over 2 factorial, x minus 4 to the second. And then minus 4 factorial over 2 to the third, over 3 factorial, x minus 4 to the third. And again, that is approximately f of x there. So then our general term what we're going to be alternating, okay, starting at n equals 0 there, it's going to be positive, so we'll say negative 1 to the n for the alternating piece. Okay. And then, let's see here. We go to 2 factorial, so that would be at n equals 1, and then 3 factorial at n equals 2, and then 4 factorial at n equals 3, and so that it's going to be n plus 1 factorial there, okay. I'm going to go ahead and all these 2's, like the 2 squared, the 2 to the third, move those into the denominators there. And so that's going to be just then 2 to the n. And then n factorial. Exactly right. It's the exact thing that we're given right there, except we have to add in the n factorial as well because, you know, well, the general term for a Taylor polynomial is centered at 4, right, is going to be right? And so you can see like this piece right here will go to this piece right there. These two are the same thing. We're just kind of like substituting there if you think about it. All right. And then of course don't forget then the times x minus 4 to the n piece. Okay. So these two pieces, you know, this is like what we would normally write for the general term for any Taylor polynomial, but then for our particular case here, the nth derivative is equal to those values. So yes, Kara. Why are we able to do that?
Yeah,
so when you have a fraction kind of within a fraction here, right, you can imagine, so for example, dividing by 1 factorial. Oh, okay, you're okay, now I got it. Okay, very good. Okay, so that was letter A. All right, we got the general term, and we got the third degree Taylor polynomial, okay, for f of x. Letter B, find the coefficient of the 10th degree term of the Taylor series for f centered at c equals 4. So we want the 10th degree term, well, the 10th degree term's coefficient. Okay. So we have our general term right here. Okay. We just want the coefficient. So which part of this are we going to throw out? The x minus 4 to the n part, right? So we're just going to use, you know, if you like here, you know, negative 1 to the 10th 10 plus 1 factorial over 2 to the 10th, and then 10 factorial times 10 factorial there on the bottom. Okay. Negative 1 to the 10th will be what? Positive 1. And so 10 plus 1 is 11 factorial over 2 to the 10th times 10 factorial. And we can simplify a little bit further, right? Because what is 11 factorial divided by 10 factorial? Just 11, right? All over 2 to the 10th. And so there's our answer. Okay, that will be the coefficient of the 10th degree term there. Okay, that's why it's helpful to have that general term. We can use that to get that coefficient pretty easily. Okay, so why don't you guys go ahead and try letter C here. Very last thing we're going to do today here. So give it a try. Show that the third degree Taylor polynomial, so the third degree one, the one that we found up here, show that this, right, approximates f of 5 with an error less than 1/3.
So can we just find the max error, or do we have to actually solve for
You just need to find the max error, that's all. You actually just need to find the max error there. Because again, we can't find the actual value here. And don't forget to write your sentence, or your little phrase there, since f alternates and decreases in absolute value to 0. So remember, for this maximum error, you're trying to show for that next term. So if we're finding the maximum error of a third degree polynomial, that means our next term is going to be what?
4.
So you should get 5/16.
Copy and paste. It's 5/16. Yeah. Ooh, that's wrong. And this is 5. Remember, it's +1 times.
So you're just not going to take it? But what happens if you transfer or something like that? I guess you won't be doing that? I understand what you're saying. So we're still going to be reviewing them as if you were. Oh, yeah, what are you gonna do? What was that? Oh. I see it now. Very good. Okay. I understand. Gotcha. Okay. So you should get, again, so you're looking at your fourth degree term. Because that's the next term for your third degree there, right? You get 5/16, which turns out to be less than 1/3 because 15 is less than 16 when you cross multiply there, right? So we do end up with the true statement. All right. All right. These last couple of days have been doozies, but we've made it through here again. One more. Are there any questions on that work up there?